Are you ready? Did you get your coffee or whatever? Because now we're getting to the meat of of today's lectures. Here we're going to talk about Hadamard, the three Hadamard conditions. So Hadamard, this is 100 years ago. He thought a lot about mathematical physics and formulations of problems, and at that time he thought that that it only made sense to solve a problem if it was well posed. It kind of makes sense what he was trying to do, and then he defined these three criteria. For a problem to be well posed, it must have a solution. It's pretty reasonable if you're looking for a solution. You would like to ensure that there actually is a solution. Also, you want a unique solution. And it must depend continuously on data and parameters. What that means is that it's really not too sensitive to the data and to the model parameters. And then he thought that the problems that we wanted to solve in mathematical physics would all be well posed. But it soon turned out that that's not quite true. And all the problems that we will see in this course here, the ill-posed problems, violate at least one and maybe more of these conditions here. And it's not because we did anything wrong, it's just the nature of these problems in tomography or image restoration or whatever, that they are just ill-posed. They're just ill-posed. They are violating at least one of these. So anyway, let's see, what is it with these three conditions and if you violate them? So the first condition is that there must be a solution. So if you write out ax equals b, and there's no x such that you can have equality there, statisticians for many years have already fixed that problem. For example, we can compute a least square solution that minimizes the 2 norm of the residual. So just by redefining the problem, we can very often make sure that there's a well-defined solution. All right, the solution must be unique. Well, for example, when is the solution to a linear system of equations not unique? Well, if the matrix is rank deficient, you have a null space, so you have a non-unique solution there. And this is what we can fix by adding some additional requirements to the solution, typically coming from the underlying physics of the problem. For example, that you want a solution of minimum norm. So again, just by adding some additional mathematical requirements, we can deal with condition 1 and 2. So 1 and 2 are the kind of easy conditions to do something about if they're violated. But condition number 3, that's the hard one to fix. Because that means here, if it's violated, that means that small perturbations of your data can give very large perturbations of the solution. And that's actually what we saw just a few slides ago with this 3×2 problem. We perturbed the right-hand side just a little bit, and the solution moved away from 1, 1 to this 7 minus 8 solution there. So the difficult condition to do something about is number 3, which is the one that leads to ill conditioning of the problem. So this is where we have to spend most of the time in trying to understand what it's doing to us, how it's hurting us, and how to do something about that one there. Right. So I thought at this time here I should illustrate these aspects with another little problem here. Right. Man, it's maybe not very realistic, but it's a good little model problem to work with. So let's see how it goes. So the s-axis there, that represents the surface of the Earth, and we put in. So the Earth here is one-dimensional. It's a really a very simple problem here, and we have an x-axis there along an s-axis along the surface, and then at the depth d, we have put a t-axis where we put some mass distribution along that t-axis there from 0 to 1. Right. So there's some mass located along the t-axis in that interval there. Okay, and of course, if we put some mass down there, it generates a gravity field that we can measure at the surface of the Earth. And what is typically measured these days, if you talk to geophysicists, is actually the vertical component of the gravitational field, right? No, so because it's fairly easy to build instruments that can measure that. Okay, so you can measure not the strength of the gravitational field, but the vertical component of that. That's what you measure up there, and that's what I'm trying to illustrate with that arrow there pointing down. All right, and that would be the field from a particular little mass that I have put there at position t below the Earth. All right, so now we need to set up a mathematical model that tells us if we put an arbitrary distribution of mass f there along the t-axis, how can we evaluate the corresponding vertical component there of the gravitational field g at the surface? So let's do that. All right. So if we have just like a point source of mass distribution at point t, and that is f of t, then the corresponding gravitational field is given by this expression here. All right, so you multiply that tiny little contribution, f of t, with the length of this infinitesimally small length along the t-axis, then you divide by r squared, because we know that that's how gravitational field depend on the distance, right? R is the distance from the point t to the point S on the surface, right? So R is given by that equation there with the square root. And then there's a sine theta there because we measure not the strength but the vertical component. So if I just back up right there, you'll see down there on the t-axis, that's your angle theta, right? And sine theta is actually given by that ratio there, d over r. R is the distance and d is the depth. And if you plug that in, you get the next equation we see right there. So that's the contribution from one infinitesimally small mass distribution right there at point t, and to get the total gravitational field at point S, you integrate along the t-axis, and since we know that everything, all the mass lies between 0 and 1 along the t-axis, we should integrate from 0 to 1, all right? So there we go. And so if we know f, then we can evaluate g by means of that equation there, right? We can do that. That's called the forward problem. So there's something down there, and if we know what it is, we can evaluate what we would measure at the surface. That's called the forward problem. The inverse problem is, of course, to compute the function f, the mass distribution, given measurements at the surface. So what you do typically to get from the forward problem to the inverse problem is that you swap what's on the left and the right side of the equation sign, and now suddenly it's an equation you want to solve. I think there's something very fascinating there when you write it in this form here, with a known right-hand side. It's built into the language of mathematics. You say right-hand side, so because it's on the right side of the equation sign, and then it's something known, and what's on the other side is partially unknown. Here it's the f that's unknown. So when you write it in this form, every mathematician who looks at this will say, oh yeah, that's a Fredholm integral equation of the first kind, and the first thing I want to do is I want to solve it for f, right? So if we want to write that in the generic form of Fredholm integrations that we saw before, the kernel, the function of two variables s and t, is given by that ratio there, d over blah blah blah. All right. So that's our inverse problem there that we want to solve. Right, so let me do that. Now I'm jumping ahead a little bit because I have actually implemented this already in MATLAB, and I've done some computations, and in the next few weeks we'll see how to actually do this. But believe me, this can be done. Okay, so I have a very weird distribution of mass on the t-axis there at depth d, which is first a strength of 2 in some arbitrary units, and then it jumps down and it has the value 1. That's what you see on the left, and on the right you see the measured field on the surface for 3 different values of the depth. Let me just back up and remind you the depth is the d there. It's the depth from the surface to the t-axis down there. Okay, there we go. Okay, and for 3 different values of that depth we get 3 different curves, of course. One obvious thing we see is that when we put the source deeper in the ground, we get a weaker signal. Right, we would expect that. Actually, if my numerical results produced something else, there would be definitely something wrong with my computations, right? So sure enough, it has to be like that. But you also see that our measurements is certainly a very smoothed version of f. In fact, there's a discontinuity in my f that is completely gone in my measurements g. So just looking at g, there's no way from looking at that you can see that there's actually a discontinuity in my f. Of course, you can look at the curves there of g, and you would guess that probably there's more math towards one end of the t interval than towards the other end, because it's kind of this non-symmetric shape there. So at least you can infer that. But boy, you would not know from those measurements that there would be a discontinuity down there. And that's a lesson to learn already here. We'll see that when we deal with inverse problems, such kind of information typically goes away in the data that we have, or it's very difficult to reconstruct something like that. We'll look into that. We'll look into what is the actual mechanism behind that in a little while. But first, a bit more introductory stuff here. Right. So again, the kind of problems we'll be looking at here, at least in the first half of the course, are these Fredholm Integral Equations of the first kind of that form there. And again, I remind you that what is known here, when we write it like that, is the right-hand side g of s. That's our data. And in fact, it may be perturbed by measurement errors or other types of errors. And then we have the function k of s comma t. It's called the kernel. And that is also a known function. That is the function that describes the system. That describes the physics of the problem we're trying to solve. And then there's the unknown. That's the function f sitting right there. Right. Okay. Later in the course, we'll actually get to look at problems in multiple dimensions. For example, when you want to do image blurring, then f is actually a 2-dimensional function, and then you see now my t is boldface. So it's a vector, and the same with the s there. Okay, but it's a fairly simple generalization, although the computational problem can get much more difficult because it gets bigger. And then there's a special case which is important. It's called deconvolution, and that is when the kernel there has a very special form where it only depends on the difference between the two variables s and t. And you can also do that in more dimensions, and we'll actually have a micro-project later on related to deconvolution. It's a very important special case. Right. Here are a few test problems that I want to show you. So from next week, we're going to be using a a software package, a MATLAB package that I wrote a very long time ago. It's called Regularization Tools. You can find it. Go to my homepage or go to MathWorks file exchange. You can find it there. This particular test problem is called Shaw. It's a 1D test problem there where the kernel is given by that strange function there. Yeah. I don't think this particular test problem, yeah, actually that comes from a physical model. You have an infinitely long slit. You send some monochromatic light through that slit. The width of the slit is precisely one wavelength, and then that integral equation there gives a relationship between the distribution of energy as a function of the incoming or outcoming angle. Right. So anyway, it's a good little test problem there, and you see that there's an illustration of that kernel, the function there of two variables. Yeah, there's not much else to say about that right now. But you notice that this kernel there is a nice and smooth function in two variables. So you would think, oh, well, that's a nice problem to solve. It's nice and smooth. Now here's another one. This is also a cooked up test problem here. If you choose that particular kernel there, that is continuous but is non-differentiable across the line t equals s, then it's very interesting here. Then the solution f to your integral equation happens to be the second derivative of your right-hand side. So this would be one way to numerically compute the second derivative. You plug it into an integral equation. That's kind of interesting, isn't it? Anyway, it's a nice little test problem here. It's not as smooth as the other one, so you might actually think that, oh man, that's probably harder to solve. We'll see whether that is true later. Now I want to discuss a really, really important mathematical result that can give us a lot of insight into what's going on, into the difficulties associated with this inverse problem here. It's the Riemann-Lebesgue lemma. I feel bad for this lemma because it's so important that it should be called a theorem. For some reason, it's called a lemma. You know, a lemma is like a little thing that you need to build up to the finale. And then the theorem is your final boss, right? And the lemma is just getting there. But man, this ought not to be a lemma. This ought to be a theorem. Anyway, okay. So let's define these functions here, which is a sine to 2p times t. T is our independent variable. And p is an integer, 1, 2, 3, so on and so forth. And of course, we can think of p as defining the frequency. The higher, the larger the p, the more oscillations you have, so you say the higher the frequency of that function there, right? Okay, then let's take that function, and there's a misprint there in the equation there. It says f, but it should be fp. We plug that in to an integral there. We multiply with some kernel. Okay, right? What kernel? Well, some k. Okay, and we evaluate that for different choices of p, and then we'll see that as p goes to infinity, that is for higher and higher frequencies, the amplitude of that function g there goes to 0. Oh, so the higher frequencies, the more damping is going on, going from f to g. And the theory says that for almost any arbitrary k function that you can think of in mathematics, this will hold. There are very, very few restrictions on k. And those restrictions that there are on k, you have to dig into functional analysis to understand that. So for the purpose of this course, this is true for pretty much any k function that we can think of. So that's quite amazing. It tells us that this is always going to happen. That higher frequencies are damped when you plug them in there, when you evaluate this integral there. And the higher the frequency, the more the damping. So somehow you know, this is a prototype of the forward problem. You plug in a function, and then you get your data. And apparently, functions f that are associated with higher frequencies will be damped a lot. And of course, what you could do is also you could take an arbitrary f, and you could do an expansion in terms of various signs with various frequencies. You could do a spectral decomposition, and then again you see that it's the higher frequencies that are damped more. So we probably expect that when we do a reconstruction, then it should be more difficult to reconstruct those high-frequency components because they are damped very much in the forward computation. So let's look at a numerical example right there. So again, that's the function we are looking at. Right. So on the left, we have fp for p equal to 1, 2, 4, and 8, and you can see higher and higher frequencies in there. And on the right, you have the corresponding g's for a particular choice of k. I don't remember what k I used there. You can see it in the book. But the point here is that you see that sure enough, the amplitude of the function g, p, gets smaller as the frequency gets higher. Right? So higher frequencies are definitely damped much more than the lower frequencies, right? Okay, so sure enough, that just illustrates the Riemann-Lebesgue lemma. Now we could try somehow to do the opposite. Maybe we could try that. Okay, so now let's start on the figure on the right. So here I have the same functions gp again, except I have scaled them such that they all have the same norm, 0.01. So now I have four different right-hand sides. They have the same norm, but they have different frequencies. And then I go back and see what's the corresponding function f, right? And of course, since the higher frequencies are damped more when you go the opposite way, it's the higher frequencies that are amplified more, right? When you solve the problem, right? So the f function corresponding to p equal 8 has the largest magnitude, and you see that, okay. So actually I wrote delta g and delta f. Why is that? Well, that's because I could think actually of these delta g's as small perturbations of my right-hand side, small perturbations of my data that I could add to some arbitrary g. And so perturbations of the right-hand side, perturbations of the data is something that is undesired, and you don't really want them, but they are there because you have that's the data you got, that's the measurements. And then you can see that high-frequency perturbations of your data give much larger perturbations of the solution than low-frequency information. So that's the point right here. If you have a low-frequent perturbation of your data, it's not that harmful. It gives a somewhat of a perturbation in your solution, but it's really not that big. But then suddenly, if you have a high-frequent perturbation of your data, then you can see the corresponding perturbation of the solution can be pretty dramatic there. Right? So that was the purpose of this illustration here, to really show you that these perturbations there, we have to worry about them. And especially the more high frequent they get, the more difficult they are to deal with. So, of course, this is a very nice, interesting mathematical exercise that students can do. But is it really relevant for engineers or other people, solving real problems? Well, of course it is. That's why we have this course here. It'll pose problems arise in so many applications. We've already seen in geophysics, in image deblurring, deconvolution, medical imaging, X-ray imaging, so on and so forth. There's so many problems that we solve routinely every day that is really an inverse problem. So, we got to find a way to deal with this, and people have done that, of course, over the years. Clever techniques to do something about this influence of the perturbations. Right. And as I've said already, in order to deal with these problems, we need to understand them. We need to understand what's going on, and we need to understand how to compensate for this sensitivity to errors. And when we discretize the problem, when we turn them into linear systems of equations we put on a computer, then we have to see how that carries over, all these difficulties and methods, how they carry over to that. We want to do that. And the core of these difficulties is really this Riemann-Lebesgue lemma. So please have that in mind. Right. So this is kind of an agenda for the rest of the course. Really, once we have formulated the inverse problem as an integral equation, say, how do we actually discretize it? How do we put it on a computer so we can solve it there? And then I've said several times that the matrix you obtain is an ill-conditioned matrix. It's always ill-conditioned. It's not because we did something wrong in the discretization. It has to be ill-conditioned. But why is that? Mm-hmm. And how come that we can still somehow compute an approximate solution? Why is that? All right. Moreover, once we have convinced us that we can do that, how do we actually do it on a computer? How do we do it efficiently and in stable fashion, so it's not too sensitive to rounding errors and stuff? Right. And yeah, what information might be available? How do we incorporate that in a solution scheme? And how do we do it? How do we do it on a computer? And once we have played around with some small problems, how do we do it for real problems, for large-scale problems in 2 and 3 dimensions? So we'll all be getting to that in a little while. But I think there's one more theoretical foundation that we need to go through before we are ready to discretize the problem. So one more theoretical insight we can do, more stuff we can do with the integral equation itself before we turn in the next lecture, next week, to how to actually put this on a computer and solve it. So what I'm going to be talking about there is something called the singular value expansion. This is really cool stuff that was invented like maybe almost 100 years ago. I do think we should take another short break right here. So we do that.